Okay guys, in this video lesson we're going to get to the next part of this unit, which deals with resistance. Okay, so if you have current flowing through a circuit, what happens is any materials that are inside that circuit, the wire, the batteries themselves, the light bulbs, the resistors themselves, anything that's inside that circuit creates some sort of resistance to that flow. Okay, so electrons don't move completely free. Okay, there is some resistance to that. Now, that resistance can be measured, and we measure that resistance. It actually can be put into equations to help us relate voltage to current. Okay, so here's how we kind of do it. So first of all, make sure we understand what resistance is. Resistance is the opposition of flow of electrons in a circuit. Okay, so it's kind of like friction. All right, it's like friction when we talk about cars and balls and stuff driving across the road, is the stuff like that. But for electrons in a circuit, that friction we call resistance. Okay, if you have more resistance, you get a bigger voltage drop, or basically there's more voltage used or a bigger energy change in a substance. Okay, that's measured in ohms. Okay, so we use the Greek letter omega to represent ohms as we do that, and it completely depends on the substance. Okay, sometimes in circuits we put in specific resistors because we want to create a voltage drop. Sometimes we deal with the fact that there is resistance, and even though we don't like it, we gotta work with it. Sometimes the device that we power, let's say it's a speaker or a light bulb or something in your cell phone, they just have some resistance to them. Okay. Now, we do use a water model for resistance also, and it's over here for us. So if you look at normal flow of current, that kind of using the idea of a water down a pipe, if we squeeze that pipe or pinch that off, that's going to stop that flow of current. So with that decrease in flow of current, you're going to get a bigger voltage drop here, and you're going to reduce your current flow during this ideas. Okay, so a kink in a pipe or squeezing down, that kind of stuff would be an idea to visualize resistance for us. All right. Now, resistance is not always a bad thing. All right. In fact, resistance is something that we need to make things work. So heating coils, any of those stoves that have exposed heating coils, like those really dark gray looking heating coils, even the ones that have glass tops, if it's an electric stove, they use resistance to heat them up. Inside your oven also, if you look inside your oven, you see glowing red hot bars. Well, the reason why they glow so hot is because of resistance. Okay, filaments in incandescent light bulbs are that way. And actually, we have resistors that look just like this, and they look kind of funny, don't they? But these are made of different materials, and those lines on there actually represent different amounts of resistance. Okay, so it's kind of it's a color code that electricians know that can identify that this resistance is different than this one, this is different than this one. But these are actually pre-designed and built resistors that go into circuitry that purposely are there to change the flow of current as part of the circuit. Okay. Now, one thing we want to make sure that we are aware of also is that wires themselves have resistance. Okay, so if you have a really skinny wire and you're trying to push a lot of electrons down that skinny wire just does not have enough space to do that. So there creates a lot of resistance there. Now, if you've ever worked with amplified audio, like maybe you put a better stereo in your car or a nicer home stereo, and you look at like buying wires to push a lot of amps to your speakers, they'll try to sell you a bigger wire, a thicker wire. And the reason why they do that is because you're pushing more electrons to create more sound in your speakers, because you need to have less resistance. So you want to have a thicker wire, especially if you want to run it a long distance. At one point in time, I put electricity to a shed that's in the end of my driveway. Not my driveway, sorry. I put electricity to a shed at the end of my property, at the back of my house. And I had to run a wire all the way out there to get electricity in there. The wire I chose to run was actually one or two sizes bigger than what it normally would be, because I had to cross my entire yard, and I knew that that length was going to create extra resistance in there. Okay, so the longer the wire, the more resistance you have, and the skinnier it is. Okay, so you want a thick wire that's really short, gives you the least amount of resistance. All right, now resistance can actually be calculated. Okay, it's calculated using something called Ohm's Law. And what Ohm's Law tells us is that the dependence of current, remember that's our I, in a conductor to the potential difference voltage and the resistance. Okay, so there's a relationship between current, volts, and resistance. And that relationship is that the current flow is a result of the voltage drop divided by the resistance. Okay, now the units we use for this is, again, our current is our amps. V is our volts, and then ohms are our resistance, okay? Now, this form of the equation is very useful for us. However, it's often described in this way instead, because often we're looking at the voltage that is inside of our circuit. So if we have a AAA battery, that AAA battery provides 1.5 volts of electric potential to our circuit. So we know that this is 1.5 volts. And that means that the current flow is going to be dependent on the amount of resistance in our circuit, okay? So what we're really saying here is that often the current flow is our dependent variable, which means we provide a certain amount of voltage, the system has a certain amount of resistance, and as a result, we have a certain current flow that goes through our circuit, okay? So of these three variables, we can physically modify voltage, we can change resistance, and because of those things that we set up or those parameters, we get a certain amount of current to flow, okay? So it's kind of our choice. That's why we have resistors we put into circuits. That's why we choose certain size light bulbs and that kind of stuff, because they create a certain amount of resistance. The power source is a type of battery that we use, creates a certain amount of voltage, and as a result, we get the right current flow through our circuit, okay? All right, guys, that is Ohm's Law. Now we're going to do a little bit of practice for us, okay? So here's two practice problems. Go ahead and pause the video here if you like and work through these two practice problems using that. And then once you're done, unpause it and we'll take a look at the solutions. All right, so here we go. First of all, our current through a toaster. Well, we're going to rearrange this equation, and we have our current flow is our 110 volts divided by our 30 ohms, and we get 3.7 amps, okay? What's nice about these equations is they're not very complex. There's no squares in here. There's no square roots. There's no adding or subtracting. It's very simple math as we work our way through. The biggest issue we usually have with students is the labeling. Okay, so make sure, remember, I is amps, voltage is volts, resistance is ohms. Those are the kind of things that people mess up, because looking at it the same way, volts divided by ohms, that equals an amp. It does. It's just not as obvious. Okay. Second one, we had 575 little m ohms, so that stands for milliohms. Remember, we can put prefixes in front of any of our units, no matter what they are, even if they're weird ones you've never seen before, and create milli or kilo or centi and that kind of stuff. So we have milliohms here. So 575 milliohms is actually 0.7575 ohms. We had 4 amps of current, so the voltage that we're going to get is 2.3 volts on this. Okay. All right, guys, we're going to end the video lesson here. In our next one, we'll do power.